Hi everyone, my name is Daniel Stilpransa, and I'm here to talk about on contraction coefficients, partial orders, and approximation of capacities for quantum channels. So I should first start by thanking my wonderful collaborators, Christoph Hirche, who, like me, is based here at the Copenhagen University, the QMAF group, and Cambyse Rouzé, who is at the Technical University Munich. So you can also find the paper which I'm going to talk about today on the archive, and you find the archive number below here. Okay, also in the description of the video. Okay, let's start by first dissecting the title. So there are a couple of terms in the title that I would like to discuss with you. So the first one is contraction coefficients. So contraction coefficients try to quantify how noisy a quantum channel is. And well, as we all know, data processing is one of the most basic requirements for any reasonable distinguishability measure. And it essentially tells us that if you apply a channel to a pair of states, any distinguishability measure should decrease under the action of the channel. This is data processing. But contraction coefficients try to provide a more fine-tuned version of data processing. That is, they try to tell us by how much we're actually contracting. So give us strict contractions. And why do we believe that this is a good way of quantifying how noisy a quantum channel is? Well, the larger the contraction coefficient, the more indistinguishable states become under it. So the more noise, in principle, you're pumping into the system. So this is already like one high level way of seeing how contraction coefficients relate to quantifying how noisy a quantum channel is. And what do we do in this work regarding contraction coefficients of quantum channels? Well, we have some structural results in the sense that we talk about contraction coefficients for general F divergences. So these are maybe one of the most general ways of formulating functionals that satisfy data processing. So we discuss a bit how do the contraction coefficients for different F divergences relate to each other, and when do we have that having a contraction coefficient for one sort of F divergence gives you a contraction coefficient for another one. But we also focus a lot on the relative entropy, not only because this is a central F divergence or distinguishability measure, it's really at the heart of quantum information theory, but also because it relates to some other themes you'll find in the title, like partial orders. So another term we have in our title are partial orders. So partial orders for quantum channels try to define a reasonable way of saying that one quantum channel is noisier than the other. So with contraction coefficients, we wanted to quantify how noisy a given quantum channel is, and with partial orders, we want to find a meaningful way of saying like, oh, this quantum channel is noisier than this other one. And if we go back to what we just discussed in the previous slide, one way of quantifying this could be saying that, you know, one quantum channel will always decrease some sort of distinguishability measure more than another. So that's maybe one way, very natural way of defining partial orders for quantum channels. But I also say it should be a reasonable way. And one of the ways of making sure that the definition is reasonable is, of course, that it has to come with an operational interpretation, or at least operational consequences, in the sense that, you know, like one channel being in some partial order larger than the other, or being less noisy in some sense than the other in an order, should also imply that that one channel is more useful in performing a certain task than the other. So it's always desirable to have some sort of operational consequence or interpretation to this partial order to make sure we're talking about something which is relevant. And what do we do in this work? Well, we define some new partial orders for quantum channels, and also very importantly, we also define approximate partial orders. So we put some epsilons around partial orders already existing in the literature. We prove some relations between some existing partial orders and also the new partial orders we introduce. We also show some new properties. And as usual, one of the big issues in quantum information theory and quantum channel theory is the issue of tensorization. So we also discuss the tensorization of existing partial orders in a bit more detail, and also the also define some new partial orders that naturally tensorize. Okay, what is the first term we have in our title? That's capacity bounds. So as most of the audience of p.1 ID probably knows, capacities quantify the ultimate rate at which you can transmit a certain resource through a quantum channel in the limit of infinitely many channel uses. And one would expect that if one has a good definition of what it means for one channel to be noisier than the other, then this should also give us some sort of capacity bound. So let's say that if channel A is noisier than channel B, you would also expect that the capacity of one is smaller than the other. So this is indeed the case for some existing bounds in the literature. And also, so what do we add here? Well, we show how some of the new partial orders we defined, and most importantly, the approximate versions, can be used to derive capacity bounds for quantum channels. And this leads to a very transparent and simple way of deriving existing capacity bounds. For instance, the ones by Zuta et al. On which they derive from approximate degradability of a channel. Okay, now that we cleared what are the main topics of this presentation, let us maybe start with the most important partial order, namely the degradation preorder. So what does it mean to say that one quantum channel degrades into another? Like in this case, we have our quantum channels N and M. It just means that we can get N from applying M, some other quantum channel to M. And in this sense, this is one way of saying that the channel is noisier, right? Because it means that we can start from M, apply some noise to it, and get M. And if you have a quantity that is monotone on the quantum channels, you will see that it will always decrease more under N than over M, as applying this extra quantum channel can only make things more distinguishable, right? Okay, and maybe this is not as well known as the characterization I gave above, but there's also an entropic characterization of degradability, which was given by Puchemi in 2016, which is this one over here, based on the min entropy. And as we'll see later, this naturally allows us to make a parallel with some other partial orders. So one could see that one can show that the one channel degrades into the other if for all outputs and a CQ state rho UAR, so we also have the reference state here R, we have the following condition for the outputs of both channels. So we see that if we have pointwise for all input states this entropic inequality, then there's also a quantum channel that satisfies this equation. And in some sense, the degradation order is the most stringent one. If you have that a quantum channel degrades into another one, then for all the orders we have, this also implies that one channel is larger than the other in that order, because most all quantities that satisfy data processing are larger for one quantum channel than the other. So in some sense, this is the strongest order. Okay, then there's also the less noisy ordering, which will be quite important in this talk. So we say that two quantum channels M and N are less noisy if there's a classical random variables and a CQ state rho UA, such that the mutual information of the outputs satisfies this relation pointwise. So recall that, and maybe to just go back to what we discussed before, you can rephrase the condition on the mutual information, which is the most common definition you see in the literature for less noisy, in the following way. So if we go back one slide, you see that we have a very similar statement over here with the min entropy and the reference system. And for the less noisy version, we have this version over here with a classical auxiliary system, and instead of having the min entropy, we actually have the von Neumann entropy. So this less noisy ordering was introduced by Watanabe in 2012, although there he was mostly interested in a channel and its complementary channels, so like not arbitrary channels M and N. And this partial ordering is well suited to the study of classical capacities, but as usual in quantum information theory, quantum Shannon theory, there are issues regarding regularization, in the sense that you have to first, like if you have this ordering for one copy of a channel, it's not a given that the same thing will hold for many copies of the channels, and we're going to discuss this issue in a bit more detail soon. But if you also want to get capacity bounds from a less noisy ordering statement, you usually also have to actually regularize this quantity, and I'll get back to that in a minute. There's another one, which is another ordering, which is called the more capable ordering. It bears many resemblances to the less noisy ordering. But here we just assume that for any ensemble with some probabilities p's and pure state psi x, we then build this corresponding CQ state here, and we demand again this neutral information bound. So if you just compare to the previous slide, we see that the structure of the states we put in is a bit different in the less noisy and more capable ordering, but they bear a lot. They have a lot in common. And yeah, as I said, it's closely related. Okay, now how do contraction coefficients actually relate to partial orders? So one of our first results is to show that if you define the relative entropy strong data processing inequality constant as follows, so we're just given some state sigma, and you fix the second argument of the relative entropy to be sigma, and then you just optimize this ratio over all possible input states rho. Okay, so this coefficient over here just quantifies how much the relative entropy contracts if you fix a second state sigma as the input of a channel, and optimize over all rows, right? And by data processing inequality, this thing will always be smaller or equal 1. And we say it's a strong data processing inequality whenever it's strictly smaller than 1. And then you can also define the less noisy domination factor, which is a similar quantity, but now instead of just restricting to rho and sigma over here, we actually also allow for a different channel in the denominator. So this is just the ratio of the relative entropies for two different channels, and we optimize over all possible input states, but leave the second argument fixed. And I think that the name we gave to this quantity, or we didn't name it actually, so I shouldn't say it, but the name here already is quite suggestive, right? Because one of our results then tell us that this mutual information formulation of the less noisy ordering is actually equivalent to the less noisy domination factor we just defined being smaller or equal than 1. So if you then defined, so in other words, if you just look at this quantity by how much the relative entropy shrinks, right? Then if you, when you, for two pairs of channels, this thing is smaller or equal than 1, then one channel is also less noisy than the other. So we can either work with this mutual information inequality, right, which was how we defined the less noisy ordering at the beginning, or we can actually work with the relative entropy contraction coefficient. Okay, and then the relation between the two words in the title, namely contraction coefficients and the less noisy ordering, become quite clear, right? Because studying contraction coefficients and studying the less noisy ordering are in principle the same thing. And usually, or there are some results in the literature where people compute less like the contraction coefficient with respect to the relative entropy. But usually there are not so many results when you only allow, like here, for the second or for the denominator to be the identity. So we're not applying anything down here. But even that scenario has a very nice interpretation. So whenever you have a contraction coefficient for a given channel, this immediately translates into a less noisy statement for an erasure channel. So if you have that the contraction coefficient of some quantum channel is p for some p smaller than 1, then this means that this corresponding channel is less noisy than an erasure channel with erasure probability p. So even if you contract the pure, just contract the contraction coefficient of some channel, this immediately allows you to compare to an erasure channel. Okay, let's talk about the elephant in the room, tensorization. So for classical channels, the less noisy ordering tensorizes. So this means that if I take one channel n and m, and I can show, if I take two channels n and m, and I can show that n is less noisy than m, then the same statement holds for many copies of n and m, which is the sort of statement you need to then prove capacity balance. But the spare activation of the private capacity implies that it's not true in the quantum case. So unfortunately, in the quantum case, you can find examples of two channels such that one copy, for one copy you have the less noisy ordering, but for two copies you don't anymore. And this motivates us to, so this is, so as a consequence, we also introduced the so-called regularized less noisy order. And this motivates another ordering, namely the completely less noisy ordering, which is an ordering that naturally tensorizes. So we, I mean, as it's also very common in quantum information theory, one way of getting tensorization is then regularizing, and another one is defining some sort of complete version of the quantity, which means that you act with the identity on some reference system. I mean, that's the general philosophy of defining a complete version of a quantity, right? So let's be a bit more precise. I mean, for the regularized, less noisy version, I'm not gonna write down what the exact definition is. It just means that, you know, like the channels are less noisy in the limit n going, I mean that the limit of n going to infinity, the two channels are less noisy. And you can just characterize that in terms of the mutual information or the contraction coefficients as we discussed before. So, but in the case of the completely less noisy ordering, we also look, we actually have a new definition here, and we say that the two channels M and N are completely less noisy if for any reference system R, you have this domination of the mutual informations. Now one can show that this ordering actually tensorizes. So if you have it for one copy of the channel, you have it for as many as you want. But there we then face another issue, which is also very common in quantum Shannon theory, right? Namely that we cannot bound the size of this reference system R here. So this makes also showing that one channel is completely less noisy than the other challenging. And I must say that we also define some other orderings in the paper, but I don't want to go through them all right now because they are essentially some variations of the orderings we discussed here, which are tailored to some applications. So let's say if you want to look at some other capacities, then it makes more sense to define these other more tailored orderings. So we, for instance, define the fully quantum less noisy, the completely more capable orderings, and so on. But as a summary, so I encourage you to take a look at the paper if you are interested in the exact definitions of those orders. But here we have a quick summary of how these orders all relate to each other and whether they tensorize or not. So here on the left, we see the two orders which we know to tensorize, namely the degradable order, because I mean, of course, if you have two channels and you can map one to the other through the action of a channel, then if you take tensor powers, you just take the tensor powers of the one channel that maps onto the other and you're done. As I said before, the way we define the completely less noisy ordering, it is designed to tensorize and it does so. And as I mentioned before, the less noisy ordering does not tensorize, and the more capable orders also do not tensorize. And then there are also some other nice relations. So an arrow over here means that one order actually implies the other one. So if you have degradability, as I mentioned before, you essentially have anything you want. But for instance, the completely less noisy ordering also implies all the other orderings which are here in the, let's say, lower right part of this diagram. So you see that there are many different relations between the orderings. They're not all equivalent, and in particular, the tensorization question is quite interesting. And some of the some of the connections are still open. So for instance, we're still not sure if there's a difference between the completely less noisy ordering and the regularized less noisy ordering. And it would be pretty nice to see if these orderings are actually different. Yeah, so as I said, some of the equivalents are still not clear. But yeah, okay, so now we defined all of these different orders, and maybe we can go one step further and also define approximate orders. So here we are really inspired by work by Zuta and et al., where they defined the concept of approximate degradability. So this means, I mean, recall that degradability meant that we can map one channel to the other through a third channel. But they had the idea of only imposing this approximately. And the right way of imposing this is through a diamond norm constraint. So they call two channels approximately degradable if you can find a channel that almost maps you from M to N, right? So up to a small epsilon. And another very nice thing about this approach is that you can efficiently check this this condition over here because it's given by an STP, and it gives you some nice capacity bounds. But and now, as you know, degradability is one of the main orders. This inspired us to do the same thing for other orders, namely take some epsilon and put it in the condition. So, for instance, for the less noisy ordering, or for instance, like the completely less noisy ordering, we had this condition I discussed before on the mutual information, right? So instead of requiring this condition to hold exactly, or not exact, I mean strictly, we allow for some error epsilon here. Okay. And it's the philosophy of defining these approximate orders is the same for all the other ones I mentioned, so I'm not going to go through it in detail. But how do you come up with these approximate orders? Well, you take the usual definition, which is given by some sort of entropic inequality, right? Some domination of entropic quantities for two channels, and then you put an epsilon around this thing. So you're allowed to violate the entropic inequality by at most epsilon. So this is the philosophy of how we define the approximate orders. But of course, in the paper, you can find the exact and precise definition of all of them. And the very nice thing is that if you start from one approximate order, you can usually also get approximate versions of the other order. So remember, I showed you a couple of slides ago this diagram of how all the different orders relate. And the same sort of diagram, not exactly, but for many of the relevant connections also holds for the approximate order. So if you have one epsilon version of the ordering, you'll usually get the other one. So for instance, if you have an epsilon degraded version of two channels, then you also get an epsilon hat completely less noisy. So if you start from epsilon degraded, you get epsilon hat completely less noisy, where epsilon hat is given by this expression over here. So you get the chain of inequalities that you start from approximate degradability, you then get completely less noisy, which gives you regularized epsilon less noisy and epsilon less noisy without being regularized, right? And well, how do you prove such statements? You start from the diamond norm and you combine it with the Alekhine-Fanes winter bound for the conditional entropy. And as an immediate corollary, you get many capacity bounds from approximate degradability. And of course, if you start with a weaker notion, let's say only completely less noisy, although I must say we don't have a proof yet that the virtual orderings are strictly different, but in principle, completely less noisy, or at least we expect it to be a weaker requirement than degradability, also gives you capacity bounds, right? So one example is